somebody has seen all of the videos on the internet apart from this one, then they'll be able to see this as well. Right, so this talk is going to be about mathematical puzzles. The reason for this is that I was looking for new questions that I can ask in my engineering maths course, and we have quite smart undergraduate students, so I think they quite like to look at some of the classic puzzles in going to talk about. So I'm going to start with the well, I'm not going to start with one of the paradoxes. I'm going to start with, from my engineering maths course, you can imagine how happy I was when I was writing my course and I discovered this quote from Roger Bacon from the beginning of the university era in Western Europe. So Roger Bacon says, mathematics is important and mathematical puzzles are important because mathematics is the gate and key to the sciences. What he means, of course, is that mathematics lets in those of us that understand how to use it, and it keeps out those people that don't. And therefore mathematics is very important, which is my introduction to my applied maths course. Neglect of mathematics works injury to all knowledge, because one who is ignorant of mathematics cannot know the other sciences or the things of this world. So this is objectively absolutely true, and it's why my students like to study maths, but they also like to study maths puzzles. And the ones we're going to look at, which I might trial on them in future, we'll start with Galileo's paradox of infinity. So this is something from Galileo's book, The Two New Sciences, which he published in the year 1638. This was about 4 or 6 or something years after he was put under house arrest by the Roman Inquisition under vehement suspicion of heresy. And so he couldn't get a Roman publisher to put out his book, The Two New Sciences, but he was able to get Ludwig, something like that, Elsevier, a Dutch publisher, to print it for him. And in this book, he deals with actually what you think of as the start of proper Newtonian dynamics. That's the first of the sciences, and classical mechanics. So, So Galileo's paradox of infinity comes about because Galileo was thinking about how do we set up something which is going to become Newtonian mechanics. And his answer is, well, we can see in order to get some sort of theory for motion, we're going to need to be able to do something like differential calculus. But before we can understand differential calculus, we have to solve this problem of how many infinitesimally small points are there in a line. And the answer is, very unfortunately, there's an infinite number of infinitesimally small points in a line. That turns out to be a problem because infinity number of points is a quantity of points which has nasty problems which were not expected. And the way Galileo tried to solve this problem was that he started to address the paradox of infinity with this prototype problem. And the problem is this. This is not the problem, this is a much later painting of Galileo in front of the Roman Inquisition, generally being sarcastic to them when he shouldn't have and getting himself into trouble. The paradox of infinity, though, is this problem. So I take it as read that you know what is a positive integer. 1, 2, 3, 4, 5 are positive integers. And you know what a square number is. 1, 4, 9, 16, 25, etc. are square numbers. Like the number of infinitesimally small points in a line, there's an infinitely long list of both integers and square numbers. But one thing we can say for sure, says Galileo, is there must be more positive integers than square numbers, very simply because we can write them in a list. And we can see 1 is an integer and a square number, 2 is an integer, but positive integer, but not a square number. We can see, obviously, if we go on to infinity, there's lots more integers than there are square numbers. Clearly true. And then he got some, he must have been thinking about this for a long time, or he talked to someone really pedantic, and they came across this second argument. Okay, but for every positive integer, there's exactly 1 square number. And for every square number, there's exactly 1 positive integer, which is its square root. So that's a problem. It means that if I write my list in a different way, I say I've got 1 and 1, and then I've got 2 and 4, 3 and 9, 4 and 16, and so on. And if I write my list this way, they're always the same length. And so it looks like there can't be more positive integers than square numbers, and there can't be more square numbers than positive integers. There must be the same number of each other. Oh dear, this is what gets to contradiction, which is written in modern notation as this unhappy face. That this is a catastrophe of reasoning. So contradiction is one of the roadblocks you really don't want to hit when you're doing some reasoning. And so in order to set up how do we do dynamics, Galileo therefore had to invent this new rule. He said, I've got a solution. These words more, less, and equal can be successfully used to compare the size of finite lists, but you mustn't use them to compare infinite lists. That's just going to cause problems. And then, of course, it takes people a lot longer to come up with more sophisticated ways of saying, are there more integers or square numbers? Galileo's answer, this is the good answer, this is the safe answer. You shouldn't say there's more or less in one infinite list than another. You won't get into trouble that way, it's just you won't be able to solve some problems. And because modern mathematicians want to solve some problems, they say, let's not bother looking for a safe answer. Let's do a really reckless answer by inventing a very complicated and pedantic language. And it turns out that in modern mathematics, one technical term which mathematicians like is the concept of this one-to-one relationship between the integers and square numbers, on which basis, in one sense, the size of the lists of integers and square numbers, for positive integers and square, is the same. So that is the argument of cardinality from George Cantor and other more recent mathematicians. But the problem with it is that it's not without criticism, because you might look at this previous slide and say, look, it's obviously wrong, because there are more positive integers, because look, those things are not squares. And so criticism of George Cantor includes some quotes that I particularly like. Henri Poincaré, a very classy mathematician, said this: transfinite set theory is a grave disease which is infecting the whole discipline of mathematics. Kronecker, of Kronecker Delta, said that Cantor was a renegade and that he was a corrupter of youth. Well, you can't get worse than that. Ludwig Wittgenstein, who I like, said that because of this transfinite set theory, the idea there's the same number of natural numbers and square numbers, because of this transfinite set theory, maths has been left ridden through and through with the pernicious idioms of set theory. This theory is utter nonsense that is laughable and wrong. It is hocus pocus and a sickness of our time. So he was pretty critical of this theory, and maybe therefore we should try and stay with the safe advice of not mucking about with lists of infinite length unless we really have to. Okay, and then in some of the problems coming up, we'll muck about with lists of infinite length, potentially. Okay.